All right. It is 12 o'clock on Wednesday. That means it's time for an Iowa Learning Farms webinar. I'm Matt Helmers with Iowa State University, Department of Ag and Biosystems Engineering, and Director of the Iowa Nutrient Research Center. And great pleasure to help moderate this Iowa Learning Farms webinar. And so we are really fortunate to have Dr. Chad Penn with us. Chad is a research soil chemist with USDA ARS and Purdue University, West Lafayette, Indiana. And he's going to talk about phosphorus removal structures, an overview of utility and limitations. Dr. Penn talked at one of our Iowa Nutrient Research Center seminars this spring. And so if you want more detail on this, I think that was a little longer form seminar, but so you can find out more information there at the Iowa Nutrient Research Center website. With that, I'm going to turn it over to Dr. Penn, and if you have questions or comments, as usual, type those in the chat box, and we'll get those to Dr. Penn at the end of his talk. Chad, virtual floor is all yours.
All right. Thank you, Dr. Helmers. Also, I'd like to thank Elizabeth for giving the opportunity to speak to y'all. So what we're going to try to do here is I'm going to try and keep this shorter than the last talk and try and leave a lot of room for questions. And the approach I'm going for, slightly different from the last one, is I was asked to give a bit more of a practical perspective on phosphorus removal structures. So that's what I'm going to attempt. So here goes. So phosphorus removal structures, the purpose of the structures, the target is dissolved P. So there's several forms of phosphorus that's transported in flow, particulate phosphorus being that bound to sediment, and then dissolved P. P removal structures are focusing on dissolved P, and not just any dissolved P, but they're intended to go after dissolved P that's coming from high testing soils, not soils that have had manure or fertilizer recently applied to them. We call that incidental losses of phosphorus, and we have other best management practices for those, namely the 4Rs. But in this case, we're talking about high P soils that are a chronic source of dissolved phosphorus. And by high P soils, in this case, what I mean is soils that have at least 100 milligrams per kilogram of maleic-3 phosphorus. So not a whole lot of soils. These are hot spots that are chronic sources. So why is it targeted to dissolved P? Well, it's because it is a more potent eutrophication agent than particulate phosphorus. Again, particulate phosphorus is that P that's bound onto sediment, and the deal is that aquatic organisms, they can immediately uptake dissolved phosphorus from water. It's immediately bioavailable. Plants can start to grow. That's not true for particulate phosphorus. Their bioavailability depends on the conditions of the water body. It depends on the characteristics of the sediment, its mineralogy, pH, things like that. So some sediment that contains phosphorus may not release any P at all. It may release, a portion of it, could release all of it, but it really depends. Some sediment can actually absorb dissolved phosphorus from the water column. So its bioavailability is generally much less than dissolved phosphorus. Okay, another reason why the structures focus on dissolved P, particularly from high P soils, is because your high P soils, which are often coined, they're called legacy phosphorus soils, they tend to stay elevated in phosphorus for many years, even after you cease from applying phosphorus fertilizer to them. So for example, this is some data from the Eastern Shore of Maryland, where they built up their soil test P level up to different levels, all the way up to nearly 600 milligrams per kilogram of maleic-3. And then they cut off all P applications and began drawing it down with the corn, wheat, beans rotation. And what they found is that, and there's other studies that have shown this as well, but if your soil test P levels are anywhere around 300 to 400 milligrams per kilogram of maleic-3, then it's going to take between 20 and 30 years for them to be drawn back down to safe levels again, to agronomic levels. And the problem, and that's a necessary thing. Drawing phosphorus down from these soils is the ultimate solution to that problem. But the problem is that in the meantime, don't wait in that all those many years, decades sometimes, you're still losing phosphorus while you're drawing it down. Every time you get a flow event, you lose a little bit of dissolved phosphorus. And that's the general impetus. Those two reasons are why the P removal structure was developed. And so what they are is very simply, they're nothing more than large landscape scale filters. And like any filter, they contain a filter media that has a high affinity for the constituent, in this case for dissolved phosphorus. And there's a lot of different types of materials. I'll briefly mention that, but essentially you channel water through the filter media, it absorbs the phosphorus, and you have a lesser concentration coming out on the other end. And then that media is able to be replaced when necessary. So that's pretty broad. Filter is a landscape scale filter is a pretty broad idea, but in general, there's three necessary components. These structures can be very diverse in appearance, but they all have some three things in common. They have an effective P-sorption material, that's your filter media, a PSM. They contain an effective PSM in a sufficient quantity. That is, they have to have enough quantity to be able to handle the runoff or drainage water flow rates. They need to be able to handle the loads, and they need to be designed such that they're in contact for a sufficient they're in contact with the water for a sufficient amount of time. Contact time is very important. So they need to be able to handle a decent flow rate. The water doesn't flow through it. You can't really treat the water. And they also need to be designed to retain and replace the PSM. You can't just throw it in a ditch and let it, or throw it in a pond or a lake or whatever, and have it simply be lost. They need to be replaced. That phosphorus that's bound needs to be removed from the system at some point. So with that in mind, you can imagine there's a lot of different ways you could build these things for a variety of different scenarios. And I'm going to present to you today just a snapshot of some examples, different ones that we built, different styles. The heart of it is the filter media, as you can imagine. There's a lot of different filter media out there. Some are better than others. Some are more expensive than others. A lot of them are industrial byproducts that work very well that you can get rather inexpensive. Metal filings, steel filings particularly, or steel shavings, steel turnings are probably one of the most economical. There's other materials as well from different industries. There are also manufactured PSMs, and they tend to be usually highly effective, but they're mostly cost prohibitive as well. I mentioned some of them are better than others, and some of them can be used. I'll mention that later. So like I said, the manufactured PSMs, they tend to be very efficient, very expensive. There's different examples commercially. You may have heard of some of these: Iron Ozorb, Imbrium, Actigard, Filtrex. So physically, the systems generally are composed of some sort of a means of distributing the inflow water, the dirty water, if you want to call it that, to distribute it among the filter media. Usually this is through perforated pipe. It doesn't always have to be. There's other ways to do it. And you have obviously a filter bed that contains your media, and then another series of drainage or collection pipes for removing the treated water from the structure. So you put water in, water flows through it, and then you have to be able to remove that water, that treated water, in order for the new untreated water to enter it. Again, perforated pipe is usually used for achieving this, but it doesn't have to be. This is kind of a generic look at what a lot of the bed structures look like. You've got, in this case, we're considering the context of a tile drain filter. I use that in this case because that seems to be a lot of the interest in Iowa and other places in the Midwest, but we've done a lot for surface structures as well. But if you can imagine your tile drain here, inflow pipe that's water is diverted. Usually we use a flow control structure to divert the water into it. More on that later. Water flows into it, and then through a manifold of some sort, it's evenly distributed, and that's important. It needs to be evenly distributed through your bed, kind of like a septic system. And then that bed, or I should say that structure containing your bed of filter media, water moves through it, phosphorus absorbs to it, the treated water goes out into a underlying manifold that mirrors the upper one, and the treated water goes out. In order to aid in designing these, while in theory they're very simple, it's just a large filter, designing them to achieve a desired flow rate and a certain phosphorus removal is a bit more involved. And so to that end, we've developed what's called the PTRAP software, Phosphorus Transport Reduction app, that is freely available from USDA, ARS. Easiest way to find it is to just Google PTRAP phosphorus. So I'd kind of like to give you an overview of several structures and also kind of discuss what's realistic and what's not realistic. And I think one of the most important things to start with is that if a site is worth treating, that is, that there's enough dissolved load on a site that it's worth removing, then it's going to require a large mass of PSM, not a small little cartridge as some of these commercialized outfits like to try and sell. So why is that? If you're going to build one that's worthwhile, it's going to have to be big. We're not talking about pounds of filter media, we're talking about tons. So why is that? Well, it's because you need a large mass of media to handle a sufficient flow rate. Keep in mind that the majority of your dissolved phosphorus is being transported during your biggest flow events with the highest flow rates. So your structure has to be designed to handle relatively high flow rates. They also have to be designed to handle a sufficient contact time. So those two things can be at odds at each other sometimes, having a high flow rate and a sufficient contact time. It can be challenging in the design. And you also need a lot of media so that it has a useful lifetime. You don't want to be changing these filters every event, or even worse, even lasting for less than an event. So all translates to needing a large mass of PSM. So because of that, the idea of cartridge filters and small modular boxes, it sounds really nice. And a lot of the commercial groups trying to sell these, that's what they go for. But it sounds nice. You got something that's portable, it's easy to install, it's kind of a plug and play. But the reality of it is it really doesn't work. It works only in very limited situations. So limited, in fact, that it's really not worth using them. And the reason why is because they contain a very limited amount of filter media, of PSM. So they can't handle a very appreciable flow rate. And if you can't handle an appreciable flow rate, you can't treat very much phosphorus. You can't remove very much phosphorus at all. Not only that, if you look at the loads coming off of some of those sites, it's much, much larger than what a small mass of media can handle. Similarly, filter socks. Filter socks are a nice idea, but they don't work for similar reasons. In fact, they're worse. Obviously, they also contain a very limited mass of filter media, and they have very poor contact between the media and water, and a low contact time. A phosphorus removal structure cannot remove phosphorus unless water flows through it. It can't just flow over the top. So you got to go big. Go big or go home, as they say, right? So how are they different from nitrogen bioreactors? It sounds similar, you got a filter buried in the ground, at least with tile drainage. The main difference is that the nitrogen bioreactors are designed to handle a much, much lower flow rate and different flow volume. With phosphorus removal structures, remember, you want to capture the high flow rates because that delivers the majority of the dissolved P. Therefore, that tends to mean that you're going to have to use a short retention time. We're talking about designing these to operate at retention times, contact times of seconds to minutes, not hours like a nitrogen bioreactor. So your nitrogen bioreactor works through biological processes. It requires a very, very long time, but as a result, it can't handle a very high flow rate either. In this case with phosphorus, we've got to be able to handle high flow rates or it's going to be fairly useless. The reason why we can get by with design these to handle high flow rates and short retention time is because these remove phosphorus by chemical processes, not biological. And the chemical processes adsorption, precipitation are much, much faster than biological processes. How are permeable structures different from wetlands? Well, wetlands are very good at reducing particulate phosphorus, that's the sediment in other words, but not dissolved phosphorus. In fact, sometimes wetlands can become a source of dissolved P, even though they're dropping out sediment and reducing total P. However, you can use wetlands in combination with a phosphorus removal structure to remove the sediment with a wetland and then treat the drainage water from it to capture the dissolved P. More on that later. There's a lot of interest from the Great Lakes Commission on that and the U.S. Army Corps of Engineers. Okay, I'll give you a quick overview of some different styles of filters that we built. This is, I call this a confined bed structure. We've built several of these in Oklahoma. I think we built some in Maryland, but essentially these treat surface runoff, and just what they say they are. It's a confined bed that contains the media. You've got essentially you need to channel the water to flow into it. In this case, we've got about 40 tons of a treated steel slag. It's aluminum coated. This is on a poultry farm in eastern Oklahoma. Very, very high dissolved P concentrations flowing into this from nearby. There's around 15, I think, poultry houses with spillage of litter around it. So very, very high dissolved P concentrations in the vicinity. And we channel the water using berms right into it. The distribution pipe at the near the surface distributes it into the media, where it drains down through into another set of perforated pipe and comes out through the expanded metal at the bottom. So this cost about $5,000. That was a while ago, though. That was about 9 years ago at this point. It handled, I need to adjust for inflation, it handled about 1,000 gallons per minute of flow. Similarly, ditch filters, they're just like the confined beds. You can treat ditch water if you have high enough concentrations in ditch water. The concentrations generally I consider to be the minimum worth treating is around 0.2 milligrams of dissolved P per liter. Although it does depend somewhat on the media, that's a good ballpark number to start with. But anyway, the ditch filters are just like the confined beds, except you have the ditch itself to confine and hold your PSM material. So it allows a large amount of PSM to be used. They're easy to build. You can see here in the ditch. So there's a dam, in this case, a flow control structure placed at a culvert at one end of the ditch. And it's underlain with a series of perforated pipe, manifold where they all collect. And then that's backfilled with your PSM, as you can see here. There's a weir in this example. So water then flows down your ditch, is held back by the flow control structure or a dam of some sort. Water drains through the media into the perforated pipe and back out. These are pretty cheap because you've already got the ditch there, generally less than $4,000. It's a good option for ditches. However, these work great on the eastern shore of Maryland, but I only recommend those in the Midwest for on-farm ditches, not the larger secondary ditches. The problem is that your downstream secondary ditches fill up with water. If you try to build one there, it's likely for the PSMs to just be washed out. So for secondary receiving ditches, instead consider a ditch bypass filter where, all right, so we have get your primary on-farm ditches. Here's your secondary ditches, obviously much larger, carry a larger, higher flow rate. Imagine diverting that water into a stormwater basin. And you build that basin into a phosphorus structure, and then after treatment, water is able to flow, rejoin the ditch again. That's one possibility for your non-primary ditches in the Midwest. Another option is to build a structure in ditch using wheat pipes that essentially you use a single perforated pipe that runs through your bed, through your filter bed, that allows your base flow, your low flow base flow, to always drain through. And this prevents the ditch structure from excessively damming or backing water up upstream. Obviously, the ditches are there for a reason. They need to drain. But then during storm flow, you see with your dam placed here, water rises, enters into the distribution pipe into the bed of media, and it drains through, is filtered by the media just like any permeable structure. and continues on through the ditch. You have a dam on the other side as well, but under regular to completely drain through those wheat pipes, through a single perforated pipe, the blue pipe in this case, that runs right through, or sorry, a solid pipe. I call it a perforated pipe. A solid pipe that runs right through the bottom and the center of the bed in order to keep the base flow moving. We haven't built one of these yet. This is just a suggestion if anyone is interested in building one on a non-primary ditch. Blind inlets are a really good opportunity to build a pyramidal structure. A blind inlet, as is, that is a traditional blind inlet, is not a pyramidal structure. It removes sediment. Essentially what it is, for those of you who aren't familiar with it, is when you replace these tile risers in your depressions in your field. So a lot of people call them prairie potholes, but anyway, these depressions in the field that accumulate a lot of water, they're often drained with these risers, the Hickenbottoms. You replace those with a bed of media. And the reason why that's done is because this Hickenbottom riser serves as a short circuit for surface water to go into the tile drainage system. So all your sediment, any suspended sediment, nutrients go straight into that Hickenbottom riser, and you've lost it. So instead, if you imagine replacing that with a bed of gravel and media underlain with perforated pipe, it provides the opportunity to filter out sediment before entering the tile drainage system. So they work very good at removing sediment, but they do very little to nothing for dissolved P. And that's because the gravel that's used, typically limestone gravel or whatever is locally available, it doesn't have an affinity for dissolved phosphorus, so it's not going to dissolve P. However, if you modify that, so if you imagine in your blind inlet filter media, if you amended this with some sort of a P-sorption media or replaced it with a P-sorption media, then now your blind inlet kind of has a dual purpose. It can serve as a phosphorus removal structure. And so we've built several of those. First one we built was we used steel slag at the surface, and it worked pretty good. Built in 2016, by 2018 it removed greater than 46% of the dissolved phosphorus load. It also removed various herbicides as well. So last summer we replaced the media in this blind inlet with a steel shavings gravel mixture. This is what it looks like, your rusty steel shavings, 8% by weight mixed with the gravel. That's what it looks like now. This should remove even more dissolved phosphorus than the steel slag did, and last much longer. So these are cheap. Blind inlets are probably, or I should say, a modified blind inlet is probably the most inexpensive, cost-effective way to remove dissolved phosphorus as a phosphorus removal structure. There is one built locally to you. This one is near Ames. This was built by Dr. Supir and Kalita, and a graduate student named Adam Busman helped to complete this one. I helped design this. We used the P-Trap software to design it. And this was on a prairie pothole that's known as Walnut. It was installed in July 2021, and it used a gravel metal shavings mixture as well, same as what I had in the previous slide. And we designed it to remove 40% of the 15-year cumulative dissolved P load based on the current loading that they had data for. And it worked very well. However, recently, there was a problem with the clogging. And what happened was that we think, it's being investigated right now, but this has happened before in Maryland with a couple of structures, a couple of blind inlets. Happens with the choice of sand that's used as the cap of the blind inlet. So, look at the anatomy of the blind inlet. You got your perforated pipe at the bottom that's connected to your tile drain, backfilled with your gravel, mixed with your PSM, and then you have a geotextile layer that helps keep sediment out of the system, and that's backfilled on top with a layer of usually sand. And the problem is, one thing we've learned is that not obviously not all sand is created equal. What some people consider to be sand is actually contains a lot of fine clay particles in it. And those clay particles will redistribute themselves and fill the pore space up between the sand particles just right, and it'll clog it. And this has happened several times, and I suspect that is what happened to the in the blind inlet in the Walnut Depression. So if you want to be cautious, which is what I do, I don't like to use sand as the capping layer for my blind inlets. I like to use gravel. Okay, it's not going to remove quite as much sediment, but there's less risk of clogging. So be cautious about that. Tile drains. So we can build these filters on tile drains. If you imagine building a buried bed of PSMs to intercept the water in the tile drain before it drains out to a ditch. And we can design these to flow from the top downward or from the bottom up, depending on the amount of hydraulic head that you have and how deep your ditch is and what the distance is between your outlet and the bottom of the ditch. I'll give you some examples. This is one. We built a lot of these in Ohio. This one flows from the top down. So here you can see the drainage layer at the bottom. This got backfilled with slag. The outlet of it and the manifold collects and flows out into a ditch. Here it is backfilled with slag, and we use a flow control structure to control head on it. So water flows into it. The manifold is distributed just like in a leach bed. Water drains through the slag and is filtered out. So you can build the tile drainage filters as beds like that, or you can put them in tanks. We built several in tanks. The principle is exactly the same, but instead you contain your media inside of a tank. We do this when we're using fairly expensive media, manufactured media that we're either going to recharge or it has some value to us. We need to keep it clean or to be able to replace it and take it out. So same exact principle though. You'll notice a lot of these diagrams, we use flow control structures, aggregate drains, water table control structures, whatever you want to call them. We use them to act as a diversion to force the water into the phosphorus removal structure bed and build head on it. And then it also serves as an emergency overflow. If the pier mill structure ever clogs up, or if it can't handle the flow, well, then you've got an emergency bypass built right into the system. This particular filter, we use 2 tons of activated alumina. Again, this was a manufactured media, so it doesn't take nearly as much media to treat a given load of phosphorus. And this was designed to remove 40% of the 10-year load. We're monitoring this one. It cost about $12,000. Again, more expensive, but treating surface runoff is a lot cheaper because it's at the surface. Those blind inlets are, I should say, those modified blind inlets are a lot cheaper, at around like $3,000, $4,000. When you start building filters below the surface, it tends to be a little bit more expensive. But if you're going to put it in a tank, that tends to be a large cost. One thing that saves a lot of money is through the use of a metal shavings, steel shavings mixture. I mentioned this earlier as being one of the best media as far as getting bang for your buck for phosphorus removal. But it's just steel shavings, steel turnings that are allowed to rust, forms iron oxide. That iron oxide has a high affinity for phosphorus. That is mixed with gravel, a nice wash gravel, 8% metal by weight. And we find that it has a very high capacity for removing phosphorus. We've built some of these in tanks. We built some in beds. This is an example of one we built up in Michigan on a swine farm. It's a buried bed. There's a 6-inch tile drain plugs into it. And it was designed to flow from the top down. This is the bottom part of the drainage pipe at the bottom. Here's the manifold, the outlet. So this got backfilled then with the steel shavings gravel mixture. We used a shooter truck, which are really, really nice. It's well worth the money to rent one of those. So we backfilled it, put the distribution pipe on top of it, which I recommend using PVC instead of corrugated for at least for the distribution pipe on top, because these tend to move around a little bit. But anyway, once that gets backfilled, we cover that with a tarp. That was about 50 tons of the mixture of media. covered it with a tarp and backfilled it. Not much to look at after it's built since it's underground, but a bed is a lot cheaper, and you can build them a lot bigger compared to using a tank. This costs $7,000, and it's going to remove a lot more phosphorus than a smaller mass of media that you can hold in a tank. So there's advantages and disadvantages to both. We did use a flow control structure on this to serve as an emergency bypass, and also to divert the water into the structure. As I mentioned before, you can combine this phosphorus removal structures with treatment wetlands or wascobs. Basically, anytime you're impounding water, and that water is then slowly metered out, slowly drained out, you can easily plumb that into a phosphorus removal structure of some sort. This is a diagram from a gentleman in Wisconsin. And this is something they're very interested. They've built a couple in Wisconsin that do this, and we're designing more, or are going to build more, where you've got your wetland to drop out the sediment. That water is impounded, and then as that water drains off, the overflow is plumbed into a phosphorus removal structure located somewhere below. So remove your sediment, particulate phosphorus to the wetland, dissolved peat gets removed with the peat removal structure. The advantages, I just said, basically, I'm going to repeat myself here, but the wetlands drop out the sediment and the particulate peat. It also prevents clogging of the peat removal structure by keeping sediment out of it. The wetland also provides a hydraulic buffer for surface water. So, while the peak flow might be 2,000 gallons per minute for a site, that's really, really hard to treat with a peat removal structure. You'd have to build a giant unit to be able to handle that. But with the treatment wetland, you can store that water and then slowly release it into the peat removal structure at a more reasonable flow rate. And analogously, a water table control structure can do this for tile drainage. If you can't handle the peak flow rate for tile drainage, well, a flow control structure will allow the soil to retain that water in the soil, and then slowly bleed it out into your peat removal structure at a more reasonable rate. And it also serves as an emergency bypass for in cases where it needs to drain and can't be drained fast enough. So the cost of the structures in general, it varies quite a bit, but it depends how big you're building them. It depends on the lifetime, your peat removal goal. Those are all things that are built into the design that you get to choose as a user. Is how much peat do you want to remove and how long do you want it to last. You get to choose your filter media, things like that as well. But because of that, the cost is going to vary greatly from your cheapest units, generally in the form of a modified blind inlet, to $20,000 for a larger unit. And they could go even higher if you wanted to build something that's even larger. We have some designs we'd like to do to build some county mains, some 24-inch diameter pipes, and those will cost more like $20,000 or even a little more than that. But when you look at it as a cost of phosphorus removed, dollars per pound of phosphorus removed, it's similar cost as wastewater treatment. Although it's a lot harder than wastewater treatment because we're removing dissolved peat. It's a bit more difficult, and it's a much more dilute source compared to wastewater. With the wastewater, you've got a much higher concentrations. It's a single pipe. It's not spread out over hundreds of acres. It's a lot easier to remove. So the fact that we're still in that ballpark is a good sign. Metal shavings tends to show the most promise as the most economical media, although in some cases, if you like to keep the media in a tank and not a bed, if you're talking about tile drainage and putting it in a buried tank, then activated alumina seems to be very economical as well. We're working on an economics paper to put out soon. I have a former student working on that. So a few things. There's a lot of things I could tell you, just different lessons learned, because we've had a lot of structures that have failed over the years. I built my first one around 2005, and learned a lot from the failures, probably more from the failures than from the successes. But one thing I've learned, before I came to the Midwest, I was designing and researching these for surface runoff only, and I used steel slag a lot. It worked great, worked fine for years. We built a pile of them on the eastern shore of Maryland. But then I thought I would bring this to when I came to the Midwest and started working with the USDA. I thought I would use slag because it was highly available, and we had a lot of filters fail. They clogged. What we learned was that tile drainage, because of its chemistry, is not compatible with steel slag, blast furnace slag, or electric arc furnace slag. In fact, any calcium-based P-sorption material is not going to work very well for subsurface drainage. You can use it and it'll work okay for about a year, but you're gonna have to clean it out. Eventually, it's gonna clog rather quickly. Works great for surface water. We use the steel slag for surface water, for blind inlets, which treat surface water. Works great for silage runoff, but it does not work very well at all for tile drainage. For tile drainage, I recommend especially using your aluminum-rich your iron and aluminum-rich P-sorption materials, PSMs. So if the only thing you hear today, remember that. Don't use steel slag for tile drainage water or any calcium-based media. There are a lot of details in some training modules that I'm putting together for NRCS. They are creating a certification program that'll be available on AgLearn. We're doing this in conjunction with ASA and ASA BE, and they should be done by the end of this year. There'll be several modules that explain everything in much greater detail than what I have done today, for understanding what they are, how the structures work, how to collect the proper inputs for designing them, and how to design them, how to use the design software, and a whole module, one entire module just on practical field lessons. And the last module, which is the last one I still need to make, is on disposal of spent media. So these should be done by the end of this calendar year. The peer removal structure is cost shared in some states through NRCS standard 782. The blind inlet has a separate standard. I can't recall what it is, I'm sorry. But again, a modified blind inlet is a type of peer removal structure. Okay, I hope I left enough questions here for, enough time here for questions. You contact, if you're interested in designing and building one, I help people design them all the time until the software gets out and people, until the modules get out and until people become comfortable with the software. I help people design structures all the time, so feel free to contact me. Sometimes when we're designing one, or building one rather, I invite people to come out and watch. So I'll put that on Twitter to give locations and times and things like that. There's a couple other slides here I need to throw on with regard to housekeeping. I
can do those, Chad, if you want to
say about that.
Yep, I can do those while you catch your breath, and folks can type in question. So if you need or you're watching for a CCA, continuing education unit, CEU or continuing education unit, email Liz Ripley, ejucums@iastate.edu by 5 o'clock today with your name, the name you entered to watch the webinar, and your CCA number. And then let's go put a plug in for next week's webinar, should be the next slide, which is Iowa's Abandoned Mineland Program. We have Vince Sitzman with Mines and Minerals Bureau. Kind of an interesting one. Maybe folks don't know about abandoned mines in Iowa and the program for restoration on those. So tune in next week for Vince. Chad, we did get some questions in here, and I'll make maybe one comment. When that information becomes available on AgLearn, hopefully we can make sure we share that through our Iowa Learning Farms outlet, so folks can go and review that material. So the first question is just kind of back at the beginning, kind of what causes soils to become legacy phosphorus soils?
Okay, sorry, that broke up a little bit on there. I'm going to read the question directly.
Causes
I'm sorry, could
soils
you read that again? There's
you
several
betcha.
questions listed here. Can you hear
Okay.
me
Yep.
okay?
Yeah, I can hear you great. I can hear you great. So, what
Go ahead.
causes
Could you please read
soils?
that one again? It had
Yeah.
broke up on me.
Yep. What causes soils to become legacy phosphorus soils?
Okay, yeah. So essentially, the application of phosphorus beyond the needs of the plant for several years. So phosphorus, is very different from nitrogen in that it can accumulate in the soil. Phosphorus it's much more sticky. It can bind very tightly to the soil. So you can add more than what a plant needs. Unlike nitrogen, for nitrogen, it doesn't bind very well to the soil. So if the plant doesn't use all the nitrogen you apply, it's going to be lost either through leaching or through volatilization of some sort. But that's not true with phosphorus. It will accumulate. So if you apply more than what the plant needs continuously, again and again, then for years, then what happens is the soil test P levels go up and up and up. And as it increases, the solubility in water starts to increase as well. And while that's not a big deal economically, and it's not a big for the farmer, and it's not a big deal agronomically, generally, it doesn't hurt anything, but you start to lose a little bit of phosphorus then because its solubility goes up. Every time you get a flow event, you lose a little bit. That little bit, again, it's mostly economically inconsequential, but that little bit, when it enters an aquatic ecosystem, is devastating because they have a very small tolerance for excess phosphorus before they start to explode with growth and become eutrophic. So it can be phosphorus continuously added beyond plant needs in any form. It doesn't have to be chemical fertilizer. It doesn't have to be manure. It can be compost. It can be in phosphorus over applied in a variety of forms. But usually, in most cases, it occurs through nitrogen-based application of animal manure, which typically, because of the nitrogen to phosphorus ratio in animal manure, when you apply the manure in order to meet nitrogen needs of the plant, it tends to add more phosphorus than the plant needs. And if you keep doing that year after year after year, you accumulate more and more phosphorus in the soil until eventually their soil test P, their Malic 3P levels become very high.
Okay. Next one, do the P removal structures need to completely drain like in N removal structures to avoid any unwanted gas production?
That's a great question. Not for gas production. That's not a concern. Instead, this is something I've been doing research on for the past couple of years, and currently is that when we use iron-rich media to remove phosphorus, the iron oxides work really, really good for removing phosphorus. My rule of thumb, for years has always been, make sure they drain in between events 100% if you're using an iron-rich media, an iron oxide-based media, because if it goes anaerobic, then it's possible for that iron to resolubilize, and in doing so, it can re-release some of the phosphorus that it had previously bound up. So that's one potential risk. So, and the solution to that is, you build structures that flow from the top down and completely drain. Now, that's something I'm exploring is well, how often does that really happen? Can we, for example, sometimes it's very useful to be able to design a P removal structure or build one that flows from the bottom up. In many cases in the field, it's a lot more convenient to do that because you don't have the head, you don't have the elevation drop in the field to drain it very well. So instead, you'll drop your pipe down, your tile drain down, have it flow into the bed, and then through the head of what you had going down, it'll come right back up to the elevation it came in at. But the problem then is your bed of media is saturated 100% of the time in between flow events. And so if you have an iron-rich media, it could go anaerobic. That's something we're exploring right now. I've built the first one in the field last year that flows from the bottom up with an iron-rich media. and we've done some lab work as well. So the jury's not out on that one yet. So for now, I say if you're using an iron oxide rich media, then you want it to design it to flow from the top down, so it drains 100% in between flow events. But so far, it's looking a little bit promising to be able to design them to flow from the bottom up for iron rich media.
Okay. Next, I have a couple questions along the same side. Is once that P is captured, how do we recycle it or dispose of that spent media?
Yeah. So good question. I wish we could use it as fertilizer. All right. That's what everybody wishes, but two reasons why you can't. The first reason is that the phosphorus is bound very tight to that medium, and that's why you use it in the first place, to bind it up tight. So then you say, oh well, I guess we could strip the phosphorus off of it and use it, and that's true. You can, and I've done that. I haven't done that for the purpose of gathering phosphorus to use as fertilizer. I've done it for the purpose of regenerating my media, so I don't have to purchase new media to save money doing that. So, and the reason why I say it's generally not worth it, you could do that. It's not worth it because the amount of phosphorus that you're trapping, in other words, the amount of phosphorus that's being lost from the field, of dissolved phosphorus that's being lost, is very, very small. All right, so you look at how much phosphorus is being lost in your hotspots. We're talking, half a pound of dissolved phosphorus per acre per year. That's not very much phosphorus in the context of agronomic needs. That's a lot of phosphorus that's lost in the context of an aquatic ecosystem. It's quite devastating. But in the agronomic context, half a pound, that's like, I don't know, price has probably gone up, but a year ago that was like 50 cents worth of phosphorus. It's almost nothing. So and agronomically, it's also not much as far as crop needs. Crops need 50, 60, 70 pounds phosphorus per acre, 40 pounds. Half a pound is very little. So you could do it, but it's generally not worth it. So instead, the best thing that we found that we do with them is we, depending on what the media is, it can be land applied. You don't expect any phosphorus fertility benefits out of it, but you can land apply it without causing any harm to anything. For the gravelly media, like the slag or the metal shavings mixed with the gravel, the metal all oxidizes and you don't have any metal pieces left. You just have red rocks at the end of it. Those sorts of things, the farmers like to use them to spread on like their dirt lanes, their farm roads, just as any way you would normally use gravel. The phosphorus is bound pretty tight to those.
We have, I think, time for a couple more questions, and a couple people have asked this about maybe what's a good way to know that a treatment bed might be needed. I mean, is there a certain soil test level where you might consider planning a treatment bed? And and might depend on the soil and location, but kind of a couple people have indicated if there was a certain level above which you'd expect that dissolved P, and then want to put in a treatment bed.
Yes, yeah, the higher the better. These things work better the higher the dissolved P concentration is. And that's just based on thermodynamics, and also as far as efficiency goes for trying to get more bang for your buck, going for the hottest spots. But generally, 0.2 milligrams per liter of dissolved P in solution is kind of a threshold. Sometimes you can go a little less than that, depending on the media. And that normally corresponds to a soil malic 3 level of 100 milligrams per kilogram of malic 3 phosphorus. Now, that's going to vary between soil types, but that's kind of on average, 100 milligrams per kilogram of malic 3 P, soil P, is going to give you enough dissolved P in flow to make it worthwhile. But the higher the concentrate, the hotter the soil, the better the candidate. So there's, it's sometimes it's difficult to find locations because, a lot of sites that, people that have high hotspots, they're not necessarily advertising it. And what I find is a lot of times the growers who want to volunteer to build a pre-roll structure, they generally don't need one because they're already doing good nutrient management and have prevented their soil test P levels from becoming high. So that's another thing to keep in mind. This technology is a last ditch effort. Okay, there's other best management practices that are preventative to prevent your soils from getting built up. But once they get built up really high, this is where you want to potentially build one.
And even if we put this in and we have those high soil test P soils, we still want to do good infield management, to try to bring that soil test P down as quick as we can, maybe.
Absolutely. Yeah, you still have to cease phosphorus applications and keep your sediment in place, control your erosion, and start the drawdown process. Yeah, this is more like a Band-Aid to trap the phosphorus during that process of ultimately getting to the root of the problem through drawdown.
Yeah, in the interest of time, one last question here. And can you elaborate on the reason why the calcium-based media types aren't suitable for tile drainage? You mentioned something about the chemistry of the tile drainage water.
Yeah, great question. The reason why is because tile drainage is rich in bicarbonate. And the calcium-rich media, usually being somewhat alkaline, and obviously having lots of soluble calcium, it ends up you end up wasting your calcium by precipitating calcium carbonate instead of precipitating calcium phosphate. So you want your calcium-based media to remove phosphorus by calcium phosphate precipitation, and that requires calcium to dissolve from the media to go into solution. But if you're pumping a bunch of bicarbonate into it, well, with that bicarbonate under those conditions, you're going to form calcium carbonate. So it's wasting your calcium that could have been used to absorb to precipitate phosphorus rather. And when it forms that new calcium carbonate mineral, it precipitates it in the pore space, which causes it to clog. So it's a double whammy. It's using up your calcium that you'd like to have for phosphorus, and it's clogging it. So bicarbonate is the ultimate reason why. It's very rich in tile drainage water because of all the biological activity in soils as it equilibrates with the CO2 in the soil atmosphere. You don't have nearly as much in surface runoff, which is why slag and things like that work really nice for blind inlets to collect surface water, but not tile drainage.
I said last question, but there's one more here that that the individual briefly had to step away and heard you mention silage leachate. So the question was, does it or does it not work for silage leachate?
I've never built one for silage leachate. I've designed some for some of my friends in Canada, and they're finding that it works really, really good. And one of the reasons why I believe the reason why it works so well is because silage runoff is fairly acidic. And it helps to dissolve a lot of the calcium in that slag. And again, when you've got a calcium-rich media, in order to make it work, the name of the game is that calcium has to dissolve. You can't precipitate calcium phosphate unless calcium first dissolves and gets into solution. That's not true for iron and aluminum-rich media. You don't have to dissolve iron and aluminum to get them to remove phosphorus, because phosphorus can bind to the surface of those minerals.
All right, Chad, I think we've taken enough of your time again today, which I really appreciate your willingness to help us out in Iowa again. One of these days, we're going to get you to Iowa. I think at the end of August, right, for the International Drainage.
Yeah. I'm looking forward to seeing you again. I mean, it's good to see you today, but it'll be good to see you in person again. So yeah, I'm looking forward. I'm hoping to get a chance to get out there and take a look at that blind inlet that Dr. Supir and Dr. Kalita had built as well. So yeah, I just want to mention, if any of you, I know there's other questions I wasn't able to get to, but feel free to contact me, and I'll answer questions, or if you're interested in building one, or if you have new media. I test media. I'm always interested in getting new phosphorus sorption media that I haven't discovered yet. I've discovered tons of media that way from people just sending it to me. I never heard of this stuff, and I'll run it. I'll test it. I'll do a flow through test on it, and I add it to the library of P removal curves to the software, so other people, so everyone can benefit from it. So I'm happy to help.
Okay. All right. Thanks a lot. I hope everybody has a great day, and thanks for tuning in to this week's webinar.